Imagine an eye that can generate entirely new faces, realistic paintings, or even detailed cityscapes, all from scratch. This is the world of GANs, or Generative Adversarial Networks. First introduced in 2014 by Ian Goodfellow, GANs have redefined how AI can create. A GAN is made up of two neural networks locked in a game, the generator and the discriminator. The generator creates data, images, audio, or text, and the discriminator tries to tell whether it's real or fake. As the generator gets better at fooling the discriminator, and the discriminator improves at detecting fakes, both networks push each other to perform better. Training a GAN is like a game of cat and mouse. The generator produces samples from random noise, and the discriminator evaluates them. Feedback loops between the two gradually improve performance. Over time, the generator becomes so convincing that even the discriminator can't tell what's fake. There are several major types of GANs. Conditional GANs. These allow controlled generation based on labels or conditions, such as generating an image of a cat, dog, or airplane. CycleGANs. These specialize in image-to-image translation. Think turning photos into paintings or horses into zebras. StyleGAN. Developed by NVIDIA, StyleGAN and its successor, StyleGAN 2 generate incredibly realistic human faces, many of which have gone viral as AI-generated avatars. PixPix turns sketches into photos and grayscale into colorized images. BigGAN, a powerful high-resolution model trained on large-scale datasets. But GANs aren't without challenges. One issue is mode collapse, where the generator produces only a narrow variety of outputs. Another is training instability. It's easy for one model to overpower the other, making learning collapse. To address these, researchers have introduced solutions like Wasserstein loss, spectral normalization, progressive growing, and architectural improvements. GANs have incredible real-world applications, generating high-res, photorealistic faces and fashion designs, creating deepfakes and voice mimics for both good and bad purposes, upscaling low-resolution images and videos using super-resolution GANs, synthesizing medical data for rare conditions, data augmentation in AI training pipelines, game development, art, and design prototyping. Looking ahead, GANs are being combined with other models like diffusion models and transformers to create even more controllable and scalable generative systems. They are also being regulated and studied for ethics, especially around misinformation, identity cloning, and creative rights. GANs represent a revolutionary step in how machines can learn to create. They are not just duplicating, they are inventing. And in doing so, they're giving us new ways to design, to understand data, and to push the boundaries of what artificial intelligence can be.